Hi everyone, welcome to the week 3 tutorial. Last tutorial we saw we had a tutorial on Word2Vec, and there we used PyTorch for some of our explanations. So we thought that we are gonna give an introduction to PyTorch itself, the framework. So in today's tutorial we are going to have a notebook on PyTorch fundamentals, and why do we use PyTorch, what capabilities does it have, and so on and so forth. So let us get started with the tutorial. So as you can see, I have connected the notebook. And so what is PyTorch? PyTorch is an open source machine learning and deep learning framework. What can PyTorch be used for? PyTorch allows you to manipulate and process data and write machine learning algorithms using Python code. Now who uses PyTorch? Now PyTorch is by Meta, Facebook, and it is used by Tesla, Microsoft, and various other deep learning labs such as OpenAI, Claude, the Anthropic, and to power research and bring machine learning to their products. So why use PyTorch? Now machine learning researchers love using PyTorch, and as of February 22, PyTorch is the most used deep learning framework on Papers with Code, a website for tracking machine learning research papers and code repositories attached with them. So PyTorch also helps take care of many things such as GPU acceleration behind the scenes. So we can focus on manipulating data and writing algorithms, and PyTorch will make sure that it runs fast. So what is today's agenda? Today we are going to cover introduction to tensors, creating tensors, getting information from tensors, manipulating tensors, dealing with tensor shapes, indexing on tensors, mixing PyTorch tensors with NumPy, reproducibility, and running tensors on GPU. So first we would like to import PyTorch. So this gives the version of the PyTorch that is in Colab. So it is 2.5.1 with a CUDA 12.1. Now introduction to tensors. Now that we have got PyTorch imported, it is time to learn about tensors. So tensors are the fundamental building blocks for machine learning. So their basic job is to represent data in a numerical way. For example, you could represent an image as a tensor with shape 3 cross 224 cross 224, which would mean number of channels, height and width. So number of channels is basically RGB, the red, green, blue, with a height of 224 pixels, which can be seen here visually, and the tensor representation of the image with shape 3 can be seen here. So in tensor speak, or the language that is used to describe tensors, tensor would have 3 dimensions. Here for the image we would have 3 dimensions, one for the color channels, height and width. So let us learn more about by coding them. It is the best way to learn about anything in computer science at least. So PyTorch loves tensors, and there is a whole documentation page dedicated to it. So if we go here, we can see the PyTorch documentation page. PyTorch documentation is pretty good and it is pretty well documented. Everything is well documented here, as you can see. So go ahead and take a look in the PyTorch documentation if you want to learn more about tensors or anything in PyTorch. So the first thing that we are going to create is a scalar. a scalar is a single number, and in tensor language it is a 0 dimensional tensor. So, scalar is equal to torch dot tensor of 7. So, scalar is tensor of 7. So, this means that the scalar is a single number, it is of type torch dot tensor. You can check, now we can check the dimensions of a tensor using the ndim attribute. So, scalar is a variable. If we go ahead and take a look at scalar dot n, the number of dimensions, as you can see the number of dimensions is 0. So, it is basically a scalar quantity with 0 dimensions. A tensor with 0 dimensions is called a scalar. Now, if we want to retrieve the number, the data in the tensor, we need to go ahead and do scalar dot item. So, get the Python number within a tensor. So, as you can see, we have got the 7 out of the scalar variable with the due to using the function item. Now, let us see a vector. A vector is a single dimensional tensor, but can contain many numbers. So, as in you could have a vector 3 cross 2 to describe bedrooms comma bathrooms in your house, or you could have 3 comma 2 comma 2 to describe bedrooms, bathrooms and car parks in your house. So, let us create a vector. Vector is basically torch dot tensor 7.7. So, now let us check the number of dimensions in a vector by the same ndim function. So, vector dot ndim gives us 1. But this is strange, we have 2 numbers and 1 dimension. So, vector contains 2 numbers, but has only 1 dimension. So, there is a trick, you can tell the number of dimensions in a PyTorch has dimensions a tensor in PyTorch has by the number of square brackets outside the square brackets, and you just count on one side. So, this has only 1. So, the number of dimensions is 1. But there is another important concept about tensors, which is their shape attribute. This shape tells you how the elements inside them are arranged. So, this is a attribute shape. So, vector dot shape, as you can see, we get the vector dot size of 2. So, there are two elements in the vector variable, in the vector tensor. Now, we can also check out what are the other functions, other attributes that this vector tensor might have. For that, we call the directory function on vector. As you can see, there is a whole lot of attribute that can be performed on the on our particular tensor in PyTorch. Feel free to go through them and check out their documentation if you want to learn more. So, the above returns torch of size 2, which means that the vector has a shape of 2. This is because 2 elements are placed inside the square brackets, which is 7 comma 7. Now, let us see a matrix. So, as you can see, this is a 2 by 2 matrix. Now, let us check the n dimensions. As you can see, the number matrix has a dimension of 2. So, you can count them by the number of square brackets it has. Now, let us just check the shape. Shape is basically the number of elements. As you can see, there are number of elements along one axis. So, there are 2 cross 2, which is basically the matrix is 2 elements deep and 2 elements wide along the row and the column. Now, let us create a tensor variable which 3 cross 3. As you have already guessed, the number of n dimensions is 3. Now, let us check the shape of the tensor. Now, the shape of the tensor is 1 comma 3 comma 3. So, let us dig a little bit more into this 1 comma 3 comma 3. So, the dimensions go outer to inner, that means there is a 1 dimension 3 by 3. So, there is 1 dimension of 3 by 3. So, dimension 0 is the outermost square bracket, the dimension 1 is the next square bracket, and the third dimension is each of the rows. So, as you have guessed, in the second square bracket we have 3 tensors, and also in the third bracket we have 3 tensors. So, torch dot size 1 comma 1 comma 1 is as you can see is pictorially well given here. So, let us summarize. A scalar is basically a single number of dimensions is 0, a vector a number with a direction, a wind speed with direction dimensions is 1, a matrix a 2 dimensional array of numbers dimension is 2, and a tensor a n dimensional array of numbers can be any number. A 0 dimensional tensor is a scalar and a 1 dimensional tensor is a vector. This is a one scalar, this is a vector, and this is a matrix, and this is a tensor. Okay. Now, random numbers. So, what are random numbers? We have established tensors to represent some form of data, and machine learning models such as neural networks manipulate and seek patterns within these tensors. So, when building machine learning models using PyTorch, it is rare that you will create tensors by hand, like what we did just right now. Instead, machine learning model often starts off with a large random tensors of numbers and adjust these random numbers as it works through the data to better represent it. In essence, start with random numbers, look at the data, update the random numbers, again look at the data, again update the random numbers, and so on and so forth. So, I mean you can define how the machine learning model starts with initialization, look at the data is representation, updates is optimization by stochastic gradient descent or ADAM and all others, and it updates the random numbers. So, in each epoch we update the random numbers, so that we there is a decrease in the loss. So, we will see about them in later tutorials. Now, we can define random numbers using torch.rand and passing it the size parameter. So, let us create a random tensor of size 3 comma 4, random tensor torch.rand size equal to 3.4. So, now printing out the random tensor and the d type. D type is basically the data type of the elements that the tensor holds. As you can see, it is random tensor and the data type is float 32. If we run it again, we will get a bunch of different random numbers. The flexibility of torch.rand is that we can adjust the size to be whatever we want to. Let us create if you go ahead and torch.create size 224, 224 comma 3, as you can see the shape is this and the number of dimensions is 3. I am not printing out this tensor because it will be not very a bunch of big of matrix, a bigger tensor with a bunch of random numbers. We can also sometimes you will want to fill tensors with zeros or ones. This happens a lot with masking, when we masking is there in attention and so on and so forth. When you go into LLMs, you will want to fill tensors with zeros or ones. So, let us create a tensor full of zeros like with torch.zeros. Again the size parameter comes into play. So, torch.zeros gives us a matrix of a tensor of 3 comma 4 with the data type float 32. Similarly, we can create a tensor of ones using the torch.ones instead torch.zeros. So, this create a tensor with all ones and the data type remains same. Sometimes we want a range of numbers such as 1 to 10 or 0 to 100. You can use torch.arrange start end step to do so. Start is basically the start of the range, end is end of range, and step is how many steps in between. Let us say we take 1. In Python you can use range to create a range. In PyTorch, torch.range is deprecated as of now and may show an error in the future. So, let us see the deprecated one also. So, as you can see, you are getting a warning that it may be removed in the future release. Although we get output from 0 to 10 with step 1. Similarly, sometimes you might want one tensor of a certain type and with the same shape as another tensor, right. So, for that we can use these functions of tensors object in PyTorch like zeros like or torch.ones like, which filled with zeros or ones of the same size as input respectively. So, like 0 to 10, and we give the input here 0 to 10. So, zeros like we are getting from 0 to 9 here, but here as we can see it is filled with all zeros because we use the function zeros like. Now, let us see. So, here we saw that we were getting the data type as torch float 32. Now, there are various other data types, different data types in in PyTorch that are available. As you can see, 32 bit floating, 64, 16, 32 bit complex, 8 bit unsigned, 16 bit, Boolean, quantized, quantized 8 bit. Now, with this parameter efficient fine tuning models, the low rank adaptation, the quantized low rank adaptation algorithms, they used a quantized format of the full floating point integers, so that we can train this very large language models in a smaller GPU. That comes with the degradation of precision. So, but these low rank adaptations and quantized low rank adaptations QLORA are pretty good, and we do not see a much decrease in performance while using them. So, let us see about tensor data types. So, some are specific to CPU and some are better for GPU. Generally, if you will see torch.CUDA anywhere, a tensor is being used for the GPU. Since NVIDIA GPUs use a computing toolkit called CUDA. Most of the time we will use a 32 bit floating point, but there are also 16 bit floating point torch.16 float 16 or 64 bit floating point, and sometimes we also have like 16 bit, 32 bit and 64 bit integers. And there is also research that is coming up that we can represent these numbers using 1 bit. So, let us go ahead and code. So, this is a float 32 tensor, torch.tensor, device D type is none, defaults to none, which is float 32. Now, device is none, this is the default tensor type, and requires grad is false. So, every tensor in PyTorch has one attribute that requires grad. Requires grad is basically says that if we want to perform gradients or backpropagation through this tensor, and if it is false, we do not we are telling PyTorch backend compiler to not create a gradient out of this torch.tensor. More specifically, PyTorch does not create the backpropagation graph for this float 32 tensor. So, we are setting it to false. So, if it is set true, the operations performed on the tensor are recorded. Now, aside from the shape issues, tensor shapes do not match up. The two of the most common issues that you will come across in PyTorch data type and device issues. For example, one tensor is torch.float 32 and the other is torch.16, then you will run a tensor. So, PyTorch often likes tensors to be of the same format, or one tensor is on CPU and the other in GPU. That that you will come across an error when both of these are occurred. So, PyTorch likes calculations between tensors that are on the same device. Let us create a float 16 tensor. We just need to pass torch.float 16 here. As you can see, we are getting torch float 16. Now, once we have created tensors, you might want to get some information from them, right. So, we have seen these before, these common attributes shape, data type and device. Let us create a random tensor and find details about it. So, we create some tensor torch.rand 3, 4. So, we are printing some tensor, we are printing the shape, we are printing the data type and which device is it on. So, we will default to CPU. So, as you can see it is float 32, shape is 3, 4 and it is on CPU. Now, in deep learning data gets represented into tensors. A model learns by investigating those tensors and performs set of operations on tensors to create representations on the patterns of the representation of the patterns in the input data. These operations often a wonderful dance between addition at the bottom level is just addition, subtraction, multiplication, division or matrix multiplication. So, stacking these building blocks in the right way, you can create the most sophisticated neural network. So, these can be seen as a just like Lego pieces, and you can just build something just out of it by using only these basic operations. So, let us start with some few fundamental operations like addition, subtraction and multiplication. So, torch dot tensor 1 2 3, we add tensor to it, it adds 10 to each one of the elements. When we multiply the tensor, we get into multiply 10 by every tensor. Notice how these values end up. I mean, first you did plus 10, then you did a multiply with 10, but we did not end up with 110, 120 and 130, because this is because the values inside the tensor do not change unless they are assigned. So, if you go ahead and check the original tensor, it is 1 2 3 only. Now, it will be assigned when we do something like this, like tensor equal to tensor minus 10. So, we are assigning the changed value to the tensor variable, as you can see is minus 9, minus 8 and minus 7. Similarly, when we do a plus 10 on each of them, we get 1 2 3. So, PyTorch has a bunch of built in functions like torch.mul short for multiplication and torch.add to perform basic operations. So, when we do a torch.multiply tensor comma 10, we multiply it like this, and similarly as we saw before, we did not assign it. So, it is still unchanged. Now, element wise multiplication. So, as we can see, this does an element wise multiplication. This is basically 1 into 1, 2 into 2 and 3 into 3. Now, matrix multiplication. So, one of the most common operations in machine learning and deep learning algorithms like neural networks is matrix multiplication. So, PyTorch implements matrix multiplication functionality in torch.matmul method. The two rules for matrix multiplication are, as you already know from your high school, the inner dimensions must match and the resulting matrix has the shape of the outer dimensions. So, note that ampersand is used, at the rate is in Python is the symbol for matrix multiplication. So, let us create a tensor and perform element wise multiplication and matrix multiplication on it. So, import PyTorch, import torch equals to torch.tensor. Let us create. So, element wise multiplication would give us 1 into 1, 2 into 2, 3 into 3 between these tensors, and we get 149. Now, if we do a matrix multiplication, we get torch.matmul tensor comma tensor, we get a single scalar. This is due to the fact that 1 into 1 plus 2 into 2 plus 3 into 3 is torch.matmul is happening. Similarly, we can also use the @ symbol for matrix multiplication. Now, you can do matrix multiplication by hand, but it is not recommended because the built in torch.matmul is faster, because in the source code of PyTorch they call the CPython library, which does this matrix multiplication in C, which is much faster at the compiler level than Python. So, you can obviously do it, and you can also use this time it of the IPython of this Colab, this cool utility, where you can see how much does it take to do a operation. As you can see, it took 1.93 seconds plus 291 plus minus 291 milliseconds per loop. Now, if we do, now this was by hand, we multiply torch random 50 cross 50, and this was by hand. And if we use the torch.matmul matmul function from PyTorch, as you can see, it is 2 microseconds. So, there is a huge difference. This is due to the fact, as I told in the compiler in the source code they calling the C programming language, and which is much faster at a compiler level than Python. Now, one of the most common errors in deep learning is the shape errors, when the shape of the matrices does not match. As you can see, if we run this, you will get an error because 3 cross 2 and 3 cross 2, you can't multiply them. So, what we can do, we can make matrix multiplication what between tensor A and tensor B by making the inner dimensions match. So, one of the ways to do this is by doing a transpose. So, there is a function torch dot transpose input dimension 0 dimension 1. So, tensor dot t where the tensor is desired tensor to transpose. Let us try this. So, this is tensor A and tensor B, we are just printing it. So, as you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 7, 10, 8, 11, 9, 12, and let us print out the tensor A and the transpose of tensor B. As you can see, it has been transposed. Now, the operation works when we pass in this, but as you can see it was not, we were not able to do this here because the inner dimensions did not match. Similarly, we can also use torch.mm, which is short for matmul, to do the same. Torch.mm tensor A and tensor B dot transpose. Without transpose, the matrix rules of matrix multiplication are not fulfilled and we get errors like above. So, this is a cool visual representation of the same. You can view this in this URL. Now, neural networks. So, coming to neural networks are full of matrix multiplications and dot products. So, torch.nn.linear, if we go to the docs, you will see a very good documentation as to what this is, what are the parameters, what are the shapes, what are the variables required, and a small example in the PyTorch documentation. Module is also shown as a feed forward or fully connected layer, implements a matrix multiplication between an input x and the weights matrix A. So, it is basically y equals to x dot A transpose plus B, where x is the input to the layer and A is the weights matrix created by the layer, and this starts out as random numbers and that get exhausted as neural networks learns to better represent the data, and B is the bias term that to slightly offset the weights and the inputs, y is the output. So, this linear function you may have seen something like this in high school or somewhere else, like y equals to mx plus b, and can be used to draw a straight line. Now, let us play around with this linear layer, try changing the variables, the input features, the output features, and see what happens. Now, so torch.manual seed is basically we are so since it is the linear layer with random weights matrix, let us make it reproducible. We will see more on this in few later, more on this later, say what this manual seed does. So, torch.manual seed linear equals to torch.linear, torch.nn.linear, input features is 2, the input features matches the inner dimension of the input and the outer features is 6, describes the outer features is that describes the outer value. Now, x is tensor A that we have defined previously, output is basically linear of x which goes into this. So, input is of shape 3 cross 2, output as you can see it is basically 2 cross 6. So, it will be 3 cross 6, 1, 2, 3, 4, 5, 6. As you can see, the output tensor is of size 3 cross 6 and there is a grad fn that is associated with it. Since we did not put the requires grad equals to false, but in PyTorch requires grad equals to true is by default. Now, what happens now there is a question like what happens if you change the input features from 3 to 6, does it error? How could you change the shape of the input x to accommodate the error, I mean, and so on and so forth. Maybe you need to do a transpose, I mean just go around and think about this. So, remember matrix multiplication is all you need. So, even at the core level, this attentions and these large language models in the core, it's all matrix multiplication, and there's this cool meme about it, like what, wait, so you are telling me it's all matrix multiplications, and this is like always has been. So, let us do some operations, some aggregation operations on these tensors, like finding the mean, max, mean and sum, etc. So, now that we have seen a few ways to manipulate tensors, let us run through a few ways to aggregate them. So, let us first create a tensor with the range function, perform minimum, maximum and mean, as you can see. You may also find methods such as torch.mean require tensors to be in float 32, most common, and another specific data type, otherwise this operation will fail. Torch.max, torch.mean, float 32 and torch.sum. Now, there is something known as positional mean and max. So, you can also find the index of a tensor where the maximum or minimum occurs using torch.argmax and argmin respectively. This is helpful in case you want to know the position where the highest or the lowest value is and not the actual value itself. So, we will see more on this later in the softmax activation function. You will need to know, you will need to get around with this torch.argmax, and you need to use torch.argmin for when you are using the softmax activation function. So, let us create a tensor, and we are using torch.argmax where the maximum happens. As you can see, this is 8th where the maximum happens at the end, and torch.argmin is 0, the 10 first index. Now, let us change the data type of the tensor. So, as mentioned, a common issue in deep learning operations is having your tensors in different data types. So, if one tensor in torch.64 and another in torch.30 float 32, you might run into some errors, but there is a fix. Torch.tensor.type comes to help. We have a d type, and let us say we change the d type to float 32. Now, this is of float 32, it was in float 32, now it is in float 16. We can similarly do with int 8 tensor. So, int 8, torch int 8, as you can see the int, it is coming int 8. Now, go ahead and I would recommend spending 10 minutes scrolling through this torch.tensor documentation and code it up yourself. Now, reshaping, stacking, squeezing and unsqueezing. Oftentimes, you will want to reshape or change the dimensions of your tensors without actually changing the values inside them. To do so, there are some popular methods like torch.reshape, torch.view, stack, squeeze, unsqueeze, permute. Why any of these? Why do we need this? Because in deep learning models, all about manipulating tensors in some way, and because of the rules of matrix multiplication, if you ever got shape mismatches, you will run into some errors. So, these methods will help you make sure that the right elements of your tensors are mixing with the right elements of the other tensors. So, let us create a tensor, again arrange, let us reshape it to 1 cross 7. So, it is, as you can see, one of the dimensions has increased, it was of size 7, but it is now 1 cross 7. Now, we can also change the view with torch.view. So, torch.view and 1 cross 7, it also changes. Remember, though changing the view of the tensor with torch.view only creates a new view of the same tensor. So, this is basically the new view of the x. So, z is basically the new view of x tensor. So, changing this z will also change the original tensor. So, this is similar to what we know as call by view or call by reference, call by value or call by reference, that changing the this z is changing the x itself. This can be analogous to call by value and call by reference that we have in OOPS. Now, if we want to stack our new tensors on top of itself 5 times, we could do so by torch.stack. So, as you can see, we just stacked them. How about removing all dimensions from a tensor? We can squeeze it using torch.squeeze. Similarly, we can use unsqueeze also. It unsqueezes a particular dimension, here at dimension 0. Similarly, we can also rearrange the order of the axis using torch.permute. So, as you can see, the new shape is 224, 224 from 224 to 224, 3. Now, indexing, selecting data from tensors. Sometimes you will want to select specific data from tensors. To do so, we can do this by indexing. This is similar to indexing on Python lists or NumPy arrays. It is similar to in PyTorch. So, 1 cross 3 cross 3. Now, let us index in the first dimension. So, first dimension we would get the whole matrix. In the second dimension, we get the first element in the second dimension, which is this 1 comma 2 comma 3, and in the third dimension, if we do 0 comma 0 comma 0, we get the first element of the first row of the first tensor, which is 1 here. Now, let us get all values in the 0th dimension. So, you can do this by this. Let us get all values of 0th, all values of 0th and first dimension only, but only index 1 and 2 dimension, only index 1 of the second dimension. As you can see, it is 258 this column. Now, get all values of the 0th dimension, but only one index value of the first and the second dimension. So, 1 comma 1, 1 comma 1 is basically 5. Now, PyTorch, tensors and NumPy. Since NumPy is popular Python numerical computing library, PyTorch has some functionality to interact with NumPy, interact with it nicely. So, torch dot from NumPy ND NumPy array to PyTorch tensor. Similarly, torch dot tensor of NumPy, PyTorch tensor to NumPy array. So, this we are converting NumPy array to tensor. We can do from NumPy an array and pass it. Similarly, we change the array and keep the tensor. So, array is equal to array plus 1 and array and tensor. As you can see, the array has been 1 is added to every other element, but the tensor is kept same. Now, if you want to go from PyTorch tensor to NumPy, you can call torch.numpy. So, this is the tensor torch.ones 7 and NumPy tensor is basically torch.numpy. It creates will default to float 32 unless changed. So, from tensor to the NumPy tensor. Now, change the tensor, keep the array same. As you can see, 1 has been added to everyone, but the NumPy tensor is the same. Now, reproducibility, trying to take the random out of random. As you will learn more about neural networks and machine learning and deep learning, you will start to discover how randomness plays a part. Well, it is pseudo randomness after all, because they are designed and a computer is fundamentally deterministic. So, the randomness they create are simulated randomness. And how does this relate to neural networks and deep learning then? As we have discussed, we start off with random numbers, then do some tensor operations, trying to make them better again and again by optimization using stochastic gradient descent or ADAM or so on and so forth. Randomness is nice and powerful, but sometimes you would like to be a little less randomness, so that you can perform so that you can perform repeatable experiments. For example, you create an algorithm for achieving X performance and then your friend tries it out to verify that you are not crazy. How could they do such a thing? So, that is where reproducibility come in. In other words, can you get the same or very similar results on your computer running the same code as I get on mine? So, let us see a brief example, example of reproducibility in PyTorch. So, we are creating random 2 tensors. Now there is a equal to, we can do it directly. Does this equal anywhere, is it equal? As you can see, everywhere it's false. Just as you might have expected, the tensors came out with different values, but what if you have created two random tensors with the same values? As in, tensors would still contain random values, but they would have the same flavor. That is where torch.manual seed comes in, as in seed is an integer like 42, or but it could be anything that flavors the randomness. So, we are doing a random seed on 42, torch.manual seed, we are giving it 42, and for torch also torch.manual seed, random seed. Now, as we can see, it is random everywhere. Now, if we go ahead and let us comment it out, let us see what happens. We comment it out, let us see what happens. As you can see, it's although I mean they are not equal. Since we did a seed, they are equal. So, they have around same tensors. So, now running tensors on GPUs. So, deep learning algorithms require a lot of numerical computation, and by default these operations are done on a CPU. However, there is another common piece of hardware called a GPU, which often makes much faster at performing specific type of operations such as neural networks need, like matrix multiplications, than CPUs. So, we have a GPU in Colab right here. So, you can change the runtime type and change the change it to T4 GPU, and you would get a GPU, but it would terminate the current session, and let us say I am saving it, and this is now connecting it to the Colab GPU, the Colab free GPU that Colab gives. And if you have a GPU or not, you can do it by this command, NVIDIA SMI. This Colab, as you can see, it is connected to the GPU. So, we are running the NVIDIA SMI, and we have around 15.3 GB of GPU, as we are not running any device processes right now on GPU. So, it is giving us no processes found. Now, getting PyTorch to run on GPU. So, we check if we have a CUDA available or not by this command, CUDA is available, check for GPU. So, it is importing torch. Now, since we had this, we changed our runtime, it is giving true. So, if the above outputs to be true, PyTorch can see and use GPU. If outputs false, it can't see the GPU, and maybe you need to check some installation steps and so on and so forth. So, set the device type, device equals to CUDA if CUDA is available, else defaults to CPU. So, CUDA. So, let us check the number of GPUs we have. We have one GPU. So, this CUDA.device counts gives us the number of GPUs. Now, since PyTorch is awesome, PyTorch helps us. PyTorch can even run on Apple's M1, M2 and M3 GPUs with torch.backend with the MPS module. So, if we check, if we can check if it is as an MPS module or not using backends, MPS is available, and similarly we can set the device. Since we do not have it, it is going to CPU. Now, if CUDA is available, use CUDA. If MPS M1 if this Apple Silicon chips are available, then use MPS. If it is not, default to GPU. So, yeah. So, putting tensors or models on the GPU. So, you can put tensors on a specific device by calling toDevice function on them when device is the target device. Why do this? Because GPUs offer far faster computation than CPUs. If a GPU is not available because of your device agnostic code like this, it will run on CPU. So, as you can see, it is running on CPU. So, this is running on CPU tensor, not on GPU. When it is we are doing tensor 2 device, it's so the first was one in CPU and when we did to CUDA, it went to CUDA. If GPU is available, we would get output something like this. Now, we can put the tensors back to CPU for not hogging up GPU RAM, so that we want to do some operation later. So, if the tensor is on GPU, can't transform it to NumPy, because this has to be converted to CPU, then it can convert to NumPy, directly it can't. So, what we do is basically on GPU to CPU by calling this CPU function, then we can convert it to NumPy. As you can see, we do not get an error now. So, the above returns a copy of the GPU tensor in the CPU memory. So, the original tensor is still on GPU. Now, we can do something like free GPU. So, there are a few commands, you can check them online to free up GPU memory, but the tensor is still on GPU, as you can see. Now, there are some exercises you can do a documentation reading, perform matrix multiplication, perform some random seeds. There is a good tutorial by PyTorch itself. I recommend the quick start and the tensors section. Learn how to represent data, what is a tensor, and also there is a good GitHub library by Sasha Rush, which these are tensor puzzles. So, when learning about tensor programming like PyTorch and NumPy, instead of relying on their magic function, you can how could you do it from the first principles and clever use of broadcasting, so that you can know what you are doing, what these magic functions are doing, and write better code. So, yeah, that is all for today. We will post this on our website, and thank you.